Şimdi kayıt almaya başlasın da döküm kayıt başlatılıyor, tamam. Şimdi başlayabiliriz hocam. Kayıt da ediyor, sonra kayıttan da izleyebilirler.
Okay, thank you so much. First of all, I would like to thanks to you to invite me to present this paper, and I wish you the very successful the conference. I hope so next year you can organize again the new and also the intensity conference. I think last 4 years you are organizing this conference, I think so. Just I will give this some introduction before giving to the main results. As the note set all the real and complex sequences, and an infinitive and the set of to the boundary sequences, and see also the set of to the convergence sequences. Both sequences are the Banach spaces under this norm. We know that for the convergence sequences, all the Banach limits to coincide. But there is it's a natural question that what about the boundary sequences? This question was answered by Banach. The Banach as an application of the Banach theorem. So he defined a linear functional L on L infinity is said to be the Banach limit if it has the following properties. Which properties? There is the three properties here. One of them is this linear functional should be the positive or positive sequences. And the next one, LE equal to the 1. This is sequence 1, 1, 1. And the third one, this is the same under the shift operator. Shift operator means the operators the shifted this term of the sequences. And if all the conditions satisfied, the linear function is the Banach limit, and B is set up to all the Banach limit on L infinity. Boundary sequences is the almost conversion if all Banach limit X coincide. For example, if you consider the sequence 1, the 1, 0, 1, 0, 1, 0. So this means this sequence is is not the convergent, but is the boundary sequences, and also there's the almost convergent sequences to the 1 over the 2. Every convergent sequence is the almost convergent, but the converse is not the true as the before the mentioned sequences. So Banach, after the Banach, Lorentz extended this definition as the follows, and C had the set of to all the convergent sequences, and if this limit exists uniformly in N, so this is all the boundaries for the boundary sequences. So this is the almost convergent sequences, set of the almost convergent sequences. Here, T and X, this is the Xn plus Xn plus 2, and up to the Xn plus n, the over m plus 1. So another sequences is the Lachener sequences. By the Lachener theta kr, the k0 equal to 0, we shall mean an increasing sequences, non-negative integers with this one. And this is going to the infinity as is going to the infinity. The intervals determined by theta will be denoted by the IR, this is, and HR, this is kr minus the kr minus 1. Then this space of this Lachener strong convergence sequences was defined by the Friedman as follows, and theta, the limit exists and equal to the 0. And actually, there is a big connection between the Lachener, the space of the Lachener strong convergence, and also the strong Cesaro summability sequences. If we consider the theta equal to the 2 power r, so this sequence spaces the same after this strong Cesaro sequence spaces. Many years after, Das and Mishra the Mishra is one of the PhD students of the class. They combine the almost convergence and the Lachener sequences to define a new sequence spaces and name it Lachener almost convergence sequences as follows. And this is the almost Lachener convergence sequences spaces. This is the strong one, and this limit x is equal to the slow and the uniform in N. Rucker used the modulus function to extend the absolute sequences to the new sequence spaces as follows. The modulus function f is the function from this interval to the interval r plus to the r plus, such that the first one is f is equal to 0 if only if x equal to 0, and next one is the function is sub-additive, and the third one is f increasing, and the fourth condition f is the continuous from the right at 0. And it's easy to see that from the condition that f is the continuous of this interval. Modulus function may be bounded and also unbounded. If you consider these sequences, this is the unbounded, but if you consider that this function is the bounded. So as already mentioned that Rucker used this one to define this sequence spaces, and if you take the fx equal to the x for all the positive x, so this LF reduced to the L1 sequence spaces. Later on, Maddox used the modulus function to define, actually to extend some new sequence spaces, W0F, WF, and the W infinitive F, to extend to the strong summable to 0. Actually, the set of the strong summable sequences, the conversion to 0. And this is also strong to summable sequences and also strong to bounded sequence spaces. So to extend the Maddox extend to those sequence spaces by using the modulus function. Later on, I used the modulus function to define the strong almost convergence, and also I give some inclusion theorem and that papers. And the next concept, we are using here the matrix transformation. What is the matrix transformation? There is a matrix, infinitive matrices. This matrix is actually is the general operator from the one sequence spaces into the another sequence spaces. In here, we define here an x distribution. Thus, we say that x is the small to n if limited x is equal to n. X and Y, two sequence spaces, N and K infinite matrices. If for each X belongs to the X, the series is convergent for each N, then sequences that belongs to the Y, and we say that A maps X into the Y, and usually we are using this symbol to show that the set of the all matrices, which is maps X into the Y. And in addition, if this matrix transformation preserving to the limit, we say that this is the regular, and also we are using this symbol to denote it. So a matrix is the regular. Actually, to be regular, a matrix satisfies the following conditions, such as the conditions, this is R1, this norm should be the infinitive, and R2 limited x is equal to 0, and R which this limited x is equal to 1. If the matrix satisfies those three conditions, and matrix A is regular matrices, we say that. Connor used the matrix non-negative regular matrix summability, and he defined, actually he extended the Maddox to the result as follows. how he did, he used the matrix, infinity matrices, regular, pardon, the regular matrices, and he defined those sequence spaces. F modulus function, A and the non-negative regular summability method. So we are defining these two sequence spaces. One sequence space is this one equal to 0, and another one is this limited axis and equal to the 0. This means the limit is 0. And here, if we take the particular case like this, and k equal to the 1 over the n, when the positive n greater than or equal to the k, this is the 1 over the n, otherwise 0, that time the color, the space is reduced to those sequence spaces which is defined by the Maddox. And if we take the particular case like this way, k belongs to this interval, and at that time is 1 over the lambda n, otherwise 0. That time color sequence spaces reduced to those sequence spaces, which was defined with myself many years ago. And here lambda n is non-decreasing sequence on positive numbers and goes to the infinity, and also satisfying those conditions. And the next one, if we take the INK, if we take the INK like this way, k between this interval, that time is the INK equal to 1 over the HR, otherwise 0. At that time, the color sequence spaces reduced to those two sequence spaces. And one of them is the Lachener modulus sequence spaces, and also the Lachener F, the modulus sequence spaces, the limit is 0. If we take here fx equal to the x, that time, this n theta f equal to the n theta, and also n theta f0 equal to the n theta 0. So those sequence spaces reduced to here. 1993, one of the based students, we extended the color definition by using the almost convergence. F is modulus function, A and the non-negative regular summability. And we took here those two sequence spaces. One of them this W A hat F, and another one W A hat F0. 0 is the means the limit is the 0 there. So those sequence spaces was defined and Nuray and myself and 1993. And also it is possible to get the particular case by using those sequence spaces. For example, if we take the NK like this way, and at that time those sequence spaces it should be reduced to those sequence spaces which was defined by the pale one. If we take böyle Poisson means that k between this interval, and that time nk equal to the 1 over the lambda n, otherwise 0. That time those sequence spaces reduced to those sequence spaces which was defined by Markowski and myself. This is the new two sequence spaces, and the W we had the lambda f. This is those sequence spaces that limited axis and equal to 0, and also then in the sequence spaces limited axis and equal to the 0. So in here, if we take the lambda n equal to the n, those two sequence spaces should be reduced to this sequence spaces and this sequence spaces. And if I take k between this interval, if I take the k between this interval, that time k equal to the 1 over the HR, otherwise 0. So those sequence spaces reduce to Pelivan and the Fisher papers, which was defined as follows: and had theta f, this limited axis and equal to the 0. And the next one is the limited axis and equal to the 0. So if I take the fx equal to the x here, and that time n theta hat f reduced to the n theta hat, and otherwise this sequence space also reduced to n theta hat 0. So those are all the known sequence spaces. 1999 I defined those sequence spaces by using the modulus function. And PAK here actually is the sequence of the strictly positive real numbers. And the next sequence spaces, this sequence space, the limited x is equal to 0. And those sequence spaces actually is the generalization of the paid one papers. There is one concept here. This is looks like the Euler's function, but not the Euler's function. Phi function. If we consider the phi function, we understood a continuous non-decreasing function, fu, and defined for u greater than or equal to 0, and such that phi 0 equal to 0, and phi u greater than 0 for the positive u. And also this is going to the infinitive as u is going to the infinitive. A phi function is called non-weaker than the phi function pc if there are constant c, b, k, l greater than 0, such that this is the less than and equal to the p phi q u for all the large u. And to show this one, we are using this symbol usually, and this was it was defined by the in the references 28. And here I know that I came to my result. Phi function and the f is given. Phi function f is the modulus function, and p equal to pk sequence of the positive real numbers, and also a equal to ak the non-negative real matrices, and another one is the Lachener sequences. So the combined this one, we defined the following sequence spaces. This sequence spaces. Okay. I'm so sorry. Then the following sequence spaces that we define. This limited x is equal to the 0 and uniform in I. Again here, if I take the n and k, 1 over the n, and n greater than or equal to the k, otherwise 0, that time the above sequence spaces reduce to this sequence spaces. And I go fast. Okay, and next one, I will remind here. If x belongs to the sequence spaces, we say that the sequence is said to be Lachener almost strong if convergent to 0 with respect to the modulus f. Phi x equal to the x for all x. So the above sequence spaces reduce to these sequence spaces and form in I. If I take the fx equal to the x, at that time the above sequence spaces reduce to this sequence spaces, and if the pk equal to the p for all k, that time the above sequence spaces reduce to this sequence spaces, and A is the identical matrices, and phi x equal to x, that time the above sequence spaces reduce to this sequence spaces. And also, if I consider the A, and k equal to 1 over the n, if n equal to the k, otherwise 0, that time the above sequence spaces reduce to this sequence spaces. So I just proved the first theorem. This is actually the one kind of the inclusion theorem. Which one is the sequence space, the domain, the strong? F is the any modulus function, phi function. A real matrix, it is A, and the P equal to the Pn is a sequence of positive real numbers. And this is the Lachener sequences. So we define this sequence spaces W hat A phi F P0 sequence spaces. So this is the first theorem. If limit if R QR greater than the 1, then this sequence space is subset of this sequence spaces. This sequence spaces defined already in the above. This sequence spaces, this sequence spaces, this sequence spaces. So this sequence space is subset of this sequence spaces. And the next one, if sub R QR less than infinity, and that time actually the converse inclusion, this sequence spaces subset of this sequence spaces. If this condition satisfied, that time two sequence spaces is unequal. So there is here two inclusion the theorem, and the third one is that under this condition those sequence spaces are the same. And the next theorem, this sequence spaces n theta a phi 0 subset of the n theta hat a phi f 0. This sequence spaces subset of this sequence spaces. So already we proved the two theorem. Next part of this talk, I just mentioned about the statistical convergence and also define the new API almost Lachener statistical convergence. Statistical convergence actually was first time was given by Zeeman in the first edition of his monography published in the Warsaw 1935. And later on, this concept, statistical convergence, was defined by the Fast and the Schoenberg independently. Over the years, and under the different names, statistical convergence has been discussed in the theory of the free analysis, ergodic theory, and the number theory. Later on, it was further investigated from the sequence basis point of view and linked it with the summability theory by Friede, and the Kanner, and the Salat, and the Mursenen, and the Malkowski, and myself, and the Maddox, and the others. Two papers is very important here. One of them is the Friede paper, and another one is Salat paper. These two papers is help that to construction the bridge between the statistical convergence and the summability theory. So that's the reason those two papers is very important for the summability theory and also the statistical convergence. And also recently, generalization of the statistical convergence have appeared in the study of the strong integral summability and structure of either of the bounded continuous function on the local compact spaces. Statistical convergence and its generalization are also connected with the subset of the strong check the complexification and the natural numbers. And also, it is possible to see that in the concept of the convergence in the probability. So, the statistical convergence, it is possible to apply the statistical convergence many area. So it is very rich. It has the many.
Bir dakika canım.
It has the many rich. It has the many rich area to apply. So. Before giving to the main results, I just mention about the statistical convergence. There is the subset of the n, and n is the set of the natural numbers. This is natural density if this limit axis. And the xk, the sequence of xk is said to be statistical convergence to the number L if for each epsilon greater than 0, this limited axis and equal to the 0. So this is the definition of the statistical convergence. Another direction, any type of convergence that we call the Lachener statistical convergence was given by the Orhan and the Friede, and as follows. This xk is the real numbers. A sequence of the xk is of the real numbers said to be Lachener statistical convergence to L if for any epsilon greater than 0, this limited axis and equal to the 0. And here the absolute value denotes the cardinality of A and subset of the N. And also in that paper, Friede and Orhan proved this term inclusion theorem. Here, theta is the Lachener sequences, A is the infinitive matrices, xk is the fifth, and its sequence is xk, and phi function fu and the positive numbers epsilon greater than 0 is be given. We wrote that for all k, this sequence, these spaces. The sequences X is said to be a phi Lachener uniform statistical convergence to the number 0 if for every epsilon greater than 0, this limited axis and equal to the 0. And here we use this actually the set to show this one. We are using the usual this set usually, and also we denote by this symbol the set of the sequence of the xk, which are Lachener uniform statistical convergence to 0, and we write that this. So usually we can write this one. Here, if I take the A equal to the matrix, if I take the identical matrices and if x equal to the x respectively, then this sequence spaces reduced to this sequence spaces. This is Lachener statistical convergence, Lachener almost statistical convergence, which was defined like this way. And also, if I take to the A and K as a particular case, this one, and that time this sequence spaces reduced to this sequence spaces. This means CFI uniform statistical convergence. And another one for all, if for all I, this sequence Pn k equal to Pk Pn, if n equal to the k, this sequence spaces reduced to this sequence spaces, uniform statistical convergence, and here P equal to Pk sequence of non-negative numbers such that P0 equal to 0 and the summation equal to the Pi. And after these introductions and the definitions, we have the following theorem. If this is the before the phi, then this sequence is subset of this sequence spaces. And next and the last theorem, I think last theorem, we assume that H if Pn less than or equal to the Pn, less than or equal to Pk, less than or equal to the H, this is the infinitive. And the theorem, if a matrix A and the sub Pk equal to H, the sequence theta and the function f and the phi be given, then this is the subset of this one. And if we change the conditions in the BA, we can get to this condition, inverse condition. What is the here? F, the modulus function should be the bounded. That means if the phi function fu and the matrix A are given, and if the modulus function f is the bounded, then this is the subset of this one. So this is inverse part of this one. So And the last theorem, I think it's last theorem, let me check, yes. And the last theorem, and there is the two Lachener sequence spaces, Lachener sequences such that this is the subset of this one, and at that time limit r is going to infinity if rh the over the r less the bigger than 0. That time this sequence spaces is the subset of the sequence spaces. So this is one kind of the inclusion theorem. So this is the last part of my talk. Just I will show some references. The Connor paper was published in 1989 to Canada Math Bulletin, and and also this paper is very important. The paper was published in Analysis 1985. And also this paper, Frida and Gioran, Cioran, this is Lachener Statistical Convergence, what was published in Pacific Journal Math. And G.G. Lawrence, this is the main the papers for the almost convergence sequences. And this is some of the other paper. Rackel paper is also is very important paper for the generalization of the sequence space by using the modulus function. And Salat paper is very important. And there's other papers. And also we used to use the Wassak paper to define the FU function. So this is all my talk. Thank you very much for your attention. Hocam? Hüseyin Hocam? Hüseyin Hocam? Hocam?
Thank you for the interesting talk, Professor Dr. Ekrem Savaş.
Thank you.
Any questions? Thank you.
Okay, thank you. Thank you very much.
Thank you.
Have a good night.
Have a good
I
night.
wish you successful conference.
Kaydı kapatıyorum.